Sometimes when you are solving a system of equations, you end up with a unique solution, which means there's only one answer. For instance, if you have a system with two unknowns and two equations, then you can solve this system very easily by simple elimination. For instance, in this case, row 1 plus row 2 is going to give us a 0 in the second column, so we're going to replace row 1. So simply adding those, I get this new matrix. This stuff is kind of a no-brainer, right? So now back substitution, because it's easy. 2x equals 2, so x equals 1. Second row, that 1x, that's 1 times 1, minus 1y equals negative 1. So I'm going to move the y to the right, move the negative 1 to the left. I get y equals 2. You get a unique solution where x is 1, y is 2. By the way, if you need more practice with simple stuff like this, just make up your own problems, because the last step is always going to be taking that solution, plugging it back in to the original system to show that it is correct. So plugging in x equals 1, y equals 2. The first row is correct. Second row, sometimes the first one's right and the second one's not, so keep going. X equals 1, y equals 2, negative 1, check, circle your answer, and move on. Now, sometimes, however, you have a system that one line is a multiple of the other. In this case, if I say row 1 minus row 2, doesn't matter what I replace, I'm going to get 0, 0, right? X minus x, y minus y. And then 3 minus a negative 1. This can never be, right? Because 0 plus 0 can't equal 4. This is a situation where there's no solution. Why? Because the lines were parallel and they never crossed each other, right? Okay, last example with a 2 by 2, x plus y equals 3, and let's say 4x plus 4y. This is very simplistic, isn't it? Right? So I have 1, 1, 3, 4, 4, 12. You can see that the bottom row is just 4 times the top row. If I say minus 4 row 1 plus row 2 and replace, let's say, row 2, then I get 0, 0, 0. That's always true. What are you going to do in a situation like this? What does it mean? It means that the two lines are the exact same line. So at this level, we have to use parameterization to get the solution to this problem. The solution is the line itself. And if you were in a pre-calculus class or a college algebra class, something like that, you could get away with just writing the equation of the line, or you could get away with saying it's the same line. But at this level, we need to do something called parameterization. So I'm going to pick some other unknown whose domain is minus infinity to plus infinity, and I'm going to choose some way of representing this line x plus y equals 3 using the new parameter. So let's just start very simple. I'm going to say let x equal some other parameter. Remember that the domain is infinite, right? There's no restrictions on my domain. We're talking straight lines on a plane. So we have to watch it. I don't want to let x equal t squared, for instance. If we had a situation where they weren't just lines and x was always positive, like you had the square root of x in your equation, then you could let x equal t squared. But in this case, there should be no restrictions on my domain. Now, if x equals t, what does y equal? We'll take that equation, x plus y equals 3. Y is 3 minus x, so y is t minus 3. Using these two equations, we get the solution to our system as x is t, y is 3 minus t. I can pick any value of t, plug it in here, and that will represent every single point on the line. Now you could choose to use a different parameterization. I could have said let y equal s, and then x would equal 3 minus s, and I would have had 3 minus s and s as my solution. Okay? So everybody's answers are going to be different. But these are actually the same answer. For instance, if I choose to make, let's let t equal 3, then this gives me the point 3, 0. But in the other case, what if I let s equal 0? Then I get the point 3, 0. See? Same point on the same line, just a different way of arriving at a particular point. And that's what parameterization is all about. In this example, we have 3 equations with 3 unknowns. Usually you're going to get a unique solution, but I've set this problem up where you can see that if I multiply this row by 3, I get this row. So these are actually the same plane. If this was a -2, for instance, then these would be parallel planes. They would never intersect and I would get no solution. But what if I have just a multiple? That means these are both the same plane. So I only have 2 planes in 3-dimensional space. When 2 planes intersect, you get a line as your intersection or the solution to the system. And at this level, you have to parameterize that solution. So let's work this one out and see what happens. So I have a 1, 1, minus 1, and a 1. 2, minus 1, 3, minus 1, and then 3, 3, minus 3, 3. So I'm going to take care of the obvious business first. I'm going to say minus 3, row 1 plus row 3, and replace row 3. So I'm going to disobey my own rules here, skip the busy work because it's obvious. Row 1s and 2 stay the same, and I get 0, 0, 0, 0. So, as we move through this course, you are going to get this type of solution over and over and over again. And you're also going to have systems that have more rows than they have unknowns, lots of zeros. Or, and more importantly for this video, you're going to have systems with more unknowns than they have rows. In that case, there's going to be a whole lot of parameterization going. This problem could have been written as two equations in two variables, and you see those equations right there in this matrix. So let's reduce as much as we possibly can. I see that it's very easy to add row 1 and row 2 and get rid of the y. You know from watching previous examples that I don't really care about the diagonal and starting with the far left column or the far right column to get things in row echelon form. I just want to get as many zeros in the same column as possible. So if you're doing a 3 by 3 system, you need to get 2 zeros in the same column. That gives you 2 rows to work with to get 1 more zero. And then the problem just falls apart for you. Any 3 by 3 system should never take more than 5 steps to solve. This case, I got zeros all the way across with 1 step. So this may be cut short a little bit, but the parameterization is what's important. So let's do row 1 plus row 2. Replacing row 1, that's going to give me 3, 0, 2, 0. Row 2 stays the same, and row 3 is negligible at this point. So now I can try to reduce it a little bit more, but if I do, I'm going to lose that 0 in the top row. So at this point, what I want to do is my parameterization. So look at the top row here. 3x plus 2z equals 0. So 3x equals minus 2z. So if I let z, and you can do this any way you want, but if I let z equal t, then x is going to equal negative 2/3. All I did was divide by 3. Replace the z with the t. Now look at row 2. 2x minus y plus 3z equals negative 1. Now I'm going to see how I've solved for x here and I've solved for z here. It's easiest right at this point to isolate that y, especially since there's no fractions. So y equals 2x plus 3z plus 1. So I'm going to plug in the stuff that I found over here, the t for the z, the fraction times t for the x, and let's see what happens. I get y equals, x is minus 2/3 t, multiply that by the 2, z equals t, so plus 3t plus 1. Now, let's make that pretty by getting a common denominator. This is going to be 9 over 3. 9 minus 4 is 5. I'm going to get 5/3 t plus 1. So my solution is a line in space. I have 2 planes intersecting in 3-dimensional space. They intersect at a line, and I'm going to represent that line with minus 2/3 t. Y is 5/3 t plus 1, and z is t. And we know that the domain for t is minus infinity. Sorry, let's write it this way. to plus infinity. Now as you move through, this is going to be assumed, and you can write your answer this way. Now in this example, we have 4 unknowns and only 2 equations. So our parameterization is going to be a little bit more complicated, but that's okay. So let's look at this matrix. 2, minus 1, 4, 3, augmented with 5. Minus 1, plus 1, I already know what I'm going to do. Because it's already set up for me, I can eliminate the y by just adding the rows. I'm going to replace, it doesn't matter, I'm going to replace row 1 because it has bigger numbers in it. So when I add those 2 rows together, I get 1, 0, 2, 4, 4. Bottom stays the same. And if I do anything else at this point, oh, I see something better that I should have done. I'm glad we did this. Look at this. These are opposites and the top is doubled. These are opposite and the top is doubled. So I just wasted my time. Let's do something different. See, I make these mistakes and I leave them in the video so that you can see. Don't jump the gun, because you might can find a better way to do things. I'm going to say row 1 added to double row 2. And again, I'm going to replace row 1. So let's write out the busy work now, obeying my own rules. 2, negative 1, 4, 3, augmented with 5. Now double row 2 is negative 2, 2, negative 4, 2, and negative 2. This may work out where what I want to show you doesn't matter anymore. Let's see. 5 and 3. So that's my new row 1, 0, 1. You see, I don't really care about where the zeros are until we get to the end of things, or if we're trying to put everything in the form of an identity. Remember, the identity matrix is always square. So you're wasting your time trying to get the identity on the left if your beginning system is not a square system. Okay, so let's look and see what we have here. I can't do anything else without losing these zeros. If I try to eliminate the ones here, then these zeros go away. So I'm going to stop what I'm doing and look at what I have. So I have, let's see, y plus 5w's equals 3. So y equals 3 minus 5w. It would make sense to let the w be one of my parameters. So I'm going to let w equal, let's start with t and see where it goes. That means that y equals 3 minus 5t. Simple enough, but let's look at row 2. Row 2 says minus x plus y minus 2z plus 1 equals negative 1. So let's plug in the w, minus x plus t, minus 2z, and, oh, I did that backwards. Catch yourself. Learn how to catch yourself. Y is 3 minus 5t, and then minus 2z plus w will be plus t equals negative 1. Make it pretty. 3, I'm going to subtract from both sides. So negative 1 minus 3 is a negative 4. Negative 5t plus t is minus 4t. I'll leave it here for now. Minus 2z. So let's see here. I want to, what would be easiest? Let's isolate the x. So x equals, moving it over to the right and adding 4 to both sides. 4 minus 4t minus 2z. So in this case, I have to introduce a second parameter. I'm going to let z equal s. That means x is 4 minus, what is that supposed to be? 4 minus 4t. Let me fix what I wrote here. 4t minus 2s. This is a different kind of problem here, and my s looks like a 5. So my solution, x is 4 minus 4t minus 2s. Y is 3 minus 5t. Z is s, and w is t. So this was a wild one that required 2 parameters. Notice that you have 2 equations, but there's 4 unknowns. So you have to be super careful and do the 2. Now, an infinite number of ways to do this. So it's kind of hard when you're looking at the answers in the book that go for problems like this. But you should be able to plug in certain values of the parameters and get the same answer at the same points. So, or change the variable to make yours match the book. So when in doubt, just plug in numbers in yours that will match some of the numbers in the answer that the book gives to show that everything else lines up. All right, good luck, guys.